Good morning, everybody. Welcome to the Friday morning session. And the first speaker today is Polina Vytnova from Surrey, who will talk about dimension function of a Lagrange and Markov spectra.
Right. So in August 2020, during the pandemic in sunny Kenilworth, Mark and I were musing about computing Hausdorff dimension of limit sets. And all we know at that time was periodic point method, which requires a lot of computational resources. And it didn't seem to be very excessive to get one number to do so much computations. So we're looking for something better. And I recalled that when I was studying in Netherlands, my supervisors there showed me a paper by Konstantin Babianka, written in 1984 on computing, in fact, of the solution to Feigenbaum-Cvetanovich expression. So that was computation of the Dublin of the fixed point of the Dublin operator. And this method, as he told me, was very efficient and converges much faster than the Lanford method, which was much well known in the West. So I looked into this, and I looked further down into Babianko papers, and I figured out that one of them was on a solution of problem on Gauss. This was, as you say, in contemporary words, was a computation of the spectrum of transfer operator associated to the full Gauss map, so that full branches of the Gauss map. And the full branches of the Gauss map is, of course, has infinitely many branches. It has infinitely many periodic points of all orders. And the associated spectrum of the transfer operator in the first eigenvalue would have been impossible to compute using the periodic point method. So he clearly did something different and something very smart. So I looked into this. And from that point, about 2 months later, we managed to compute Hausdorff dimension of a large number of sets of continued fractions, a large number of contour sets of continued fractions that were far beyond reach. And in December, we put a preprint on arXiv. And about a day later, I got an email from Karl Schmatheusz and Gugu Moreira. Maybe they actually wrote to Mark at first, asking us if we can compute, if you can go even further, if we can compute some Hausdorff dimension of another contour set that at first sight appeared beyond reach. But then after some thinking, a week later, realized that it is also possible. And from this moment, this two sequence of papers started to grow, started to appear, started to emerge. So this is what I'm going to talk to you about today. And it is going to have a lot of number theories. So I'm going to start very slowly and introducing what actually the goal was and why we were interested in this kind of things. Before you start, before you pick up numbers, server run by number theories group and start to run computations there for months around the clock, that you need to do something, you think that you need to do something useful for that. All right, so I'm going to be interested in the sets which are written in terms of digits of the continued fraction expansions of their elements. So for me today, continued fraction is ordinary continued fraction. This is expression of this type, this infinite sum, the limit of this sequence. And if you have once we know what continued fraction is, we can consider also bi-infinite sequences. And we want to introduce the dynamics now. So the dynamics is going to be Bernoulli shift. And this is what Bernoulli shift does. Okay, so once we have our space and we have dynamics, we can also introduce a map related to this dynamical system and does the following. So it takes a sequence, it takes bi-infinite sequence and splits it in two halves. One is going from 0 to positive, and another is on all negative indices. And it creates two continued fractions from these two sequences. And this continued fraction is in fact a number. So it was discovered by Perron in 21. The paper is written in German, I believe, that in fact, to any sequence, you can associate a number which was already known. It was called Lagrange number, and different known from the different context. And this number is defined as the limit supremum along the orbit of the shift of the sequence that you have. And another number that you can introduce, that was also known before, but you can associate it from the works of Andrei Markov. But nevertheless, Perron proves that in fact, to any sequence, you can associate another number, which is going to be the supremum of the values of our map, lambda along the orbits. So you take a sequence, you take bi-infinite sequence, you take all possible shifts. The map lambda just splits the sequence into two bits, into positive and into negative. And you take the sum of these numbers that you obtain from continued fraction expansions. And we define two functions, if you like, or two numbers associated to a sequence. One is called Lagrange number, and another one is called Markov number of a sequence. And Lagrange number for definiteness is limit supremum along the orbit, and Markov number is just supremum along the orbit. All right. So then the union, the way I said that they were known before in the sense that number theorists studied this collection of numbers, so that all numbers that you obtain by studying different sequences, and they of course got the names Lagrange spectra and Markov spectra. And one of belong is a subset of another. So the Lagrange spectra is a subset of a Markov spectra. All right, so this is the two sets that we are going to be interested in today. Let me just write a definition in case it is useful for later reference. So I'm going to write that alpha, lambda of alpha is the limit supremum, m alpha, and m of alpha is just supremum of lambda m alpha, just in case we need it later. All right, so here we go. This two sets of the two subsets of real lines, they were introduced first in the middle of 19th century. So by the time Perron did his work, it was already 7 years these sets were studied. And here's some results. There's a bit of a history that Markov proved, after whom the numbers were named, that the spectrum in the interval from square root of the smallest number is square root of 5. And in fact, in the interval between square root of 5 and 3, this number is discrete. Sorry, this is the Markov spectrum is discrete. And but the proof he didn't know Perron's results, so he used completely different approach from this is called Markov triples. And then Hurwitz, a little bit at the same time, proved that Lagrange spectrum, the smallest number in the Lagrange spectrum is square root of 5. And his definition was via the best approximant. So if it is from the Diophantine approximation, that square root of 5 is a famous number from Diophantine approximations. Then there was some further work, the study that this set attracted a lot of attention of number theorists, and Perron proved that in addition, using his definition now, that in the interval between square root of 12 and square root of 13, the set is in fact empty. The Markov spectrum is in fact empty. But the two bounds, the two endpoints, in fact, belong to the Lagrange spectrum. So that, in fact, it is not very easy. It's not very easy to compute the exact values of Markov or Lagrange spectra. Well, in the discrete part is well known, that is quadratic rationals, but then it gets much more complicated. Okay, and he also proves that one set is a subset of another. Okay, so then some years passed, and in 1947, Hall, working in the West, in the United States, proved in fact that that exists a number which is called C here, the constant, such that the Markov spectrum contain, and both Lagrange spectra, they contain the entire array. So that in fact, they start, it is the subsets of the real lines, they start from being discrete, and at some point it becomes everywhere, everything. But this C was not known for some time until the work of Feynman in 1975. Where he claims he established the value of this constant, of this value C, and it is called now Feynman constant. So let's go into see what it looks like. This is a number. The only existing proof of the fact that this number is equal to this quadratic rational is written in Russian. It has about 120 pages, and it has never been checked and has never been translated. So if there is anybody looking who has a good master student looking in computer verification, maybe they can try. I have a copy. I have an online copy of Feynman's work. Maybe they can get a student to try to verify it, or maybe they can get a student and a computer to verify that this is exactly the right value. Feynman now is about 90 years old. I think he's over 90, and he lives in Jerusalem. Last time people asked him, at least that's the rumors I heard, is that he thinks that the constant is somewhere there. So we still don't know what exactly it is, or we have not checked that, but we have not been able to find any mistakes in Feynman's work, and we know that some number exists. Okay, so if two sets are so close to each other, a reasonable question that you may ask is whether there is anything in between, so whether they are equal or not. And indeed, few results are known by now that claim that there exist sets indeed are not the same, that the complement to Lagrange spectra in Markov spectra is by no means empty. So that first there was appeared some individual values, but in fact, this complement actually contains a lot of counter sets. That is. And now there was a lot of conjectures about the structure of these two sets, which attracted as a sort of important in number theory. And the first conjecture probably was that the complement is empty in between square root of 12 and infinity. There was also conjecture that, in fact, it's still not known whether there are any intervals before the beginning of the whole race. So we know that there exists a number C, so that both sets contain an infinite ray. What we don't know if they contain any intervals before the whole ray starts. So this is this is open to date. One of the breakthrough in this century was done by Moreira and his 2018 Annals paper, when he proved that the dimensions of two sets is the same, and it is in fact a continuous function. So it is that if we measure the dimension of the set in the interval between -infinity and t, then this function continuously depends on t, but it is not very nicely behaved. But what we don't know is that once we pass the threshold where the sets are discrete, then dimension is strictly bigger than 0. So that we know that before the 3, there is a discrete sequence of quadratic irrationals which converge to that Markov and Lagrange spectra both just is discrete set of quadratic irrationals. But this converges to 3. And now we also know that the set, in fact, has positive dimension in the subset between 3 and infinity. Both sets have positive dimensions there. Okay, so the first conjecture was broken, and it was broken several times already, that we discovered, in fact, explicit numbers that are there. So this doesn't hold anymore. And our interest for today is going to be the properties of this function, or what we are going to try to do. We are going to try to compute the Hausdorff dimension of the set of the Markov spectrum as a function of t, and we're going to be interested in the Hausdorff dimension of Markov spectrum in the interval between -infinity and t. So I'm going to pause here in case there are any questions. It's a good time to ask questions. Okay. Yes. Yes, it is in 120 pages manuscript published by Kalinin University in 1976. I have a scan version. That nobody was ever able to read it and to confirm it. Yes, the people that it has never been checked by anyone.
Thank you.
Okay. Any other questions? Okay. Yes.
Sorry, can I ask a very stupid question? Since I'm not familiar with Lagrange and Markov spectrum, what are the implications for number theory for knowing the Markov and Lagrange spectrum?
Maybe I will leave it until after the talk.
Okay.
Thank you. I had more or less the same question, like what is the meaning of this lambda of alpha?
It is a shift.
No.
So what is the meaning of this function, you mean?
Sigma
is a shift, yes.
But lambda of a continued function, what does it tell us about the continued function?
Lambda of a sequence, it helps.
Yes.
It just gives us information about well, it turns sequence into continued fraction. I think that it was introduced specifically to so it's just a tool. I don't think there's any specific meaning of this.
Thank you so much.
Okay. Any Anything else? Okay, so maybe we can progress and try to get to our business. So what we are interested in, if we need to compute something, we actually, this is a very complicated fractal set, and it would be good to have any way to access it. And it was done before us. It was okay. So let us recall. So our set is the house. This function is a house of dimensions. This is what we want. This is our first result on this function. So what we were able to do, our first interest was to establish actually when this function becomes, so when the dimension becomes full. So this is called the first transition point, and it is the point where when dimension becomes 1. And for this reason, if you're interested in a function itself, then in fact, you're restricted to very, very small interval that it is between 3 and 3.3343, that in fact is like, as we often do in fractal geometry, we study the sets of the zero measure. In this case, it doesn't have zero measure, but it is still a very tiny interval, in fact, on a real line. So the function, as I said, is nowhere close to being nice. It is a Dale staircase function, naming that it is a monotone increasing, but its derivative is equal to 0 almost everywhere. This is another couple of facts that we know about it, that, as I mentioned, that once you pass a 3, it becomes positive. And also more recent result, I'm not involved in this, that in fact, we know what the asymptotic is in 3, near 3, and it is written in terms of this Lambert function but at least it is known. So what we did, we got a graph, in fact, of this. We got a very accurate approximation to this dimension function. It looks as a Devil staircase. It has a lot of intervals of where it is constant. So what if you let's see that there is 2 curves, so it is a promise that there are supposed to be 2 curves, but they are so close to each other that on this particular picture we are not actually able to distinguish between them, but I promise there are 2 of them. And once we computed the function itself, another question that you can ask is just we want to find out how big are the intervals where it is constant. So in fact, if you know all intervals that are subsequently large, which are bigger than 5,000 in size, there are 12 of them exactly, where the function is a constant. But apart from that, it is a Devil staircase. What more one can say? Yes. When I say Devil staircase, I mean it is continuous monotone increasing, and its derivative is equal to 0 almost everywhere. Okay. So this we tried to get as accurate picture of this function as possible, and so this is just a comparison where on the right-hand side, if you have really good eyesight, you might be able actually to see that there are indeed 2 lines, so that near sometimes, especially when the function changes, like when it grows, then you can distinguish that there are indeed lower bound and upper bound. And in fact, the way that the function was computed is that we took about I took about 7,000 points in this interval, and at each of these 1,000 points, we computed lower bound and upper bound. And this way, we plotted the graph. So if you have about 1,000 points in the interval of the size 3 or 10, 3/10, then it gives you very accurate and almost convincing picture that you have a very good approximation. So this is a comparison with the Lambert function near 3. So as one can probably see that we were not able actually to approach here. So this the value when it turns to 1, and on the left-hand side, we were not able to approach the 3. And this is the sort of artifact of our method, that it requires longer and longer computations at once when you approach the limit. So that I will try to give an insight a little bit into this. But yeah, so there is this is the fact that the graph here doesn't reach 1 is sort of the problem, intrinsic problem of the method, if you like. Yes. In the intervals, in these intervals, almost all of them contain exactly 1 point. I said there are 12 of them, so almost all doesn't mean precise. So out of 12, 10 contain exactly 1 point, and everything, all others are empty. Yes, this would be precise statement that there are 10 that out of these red intervals that we found, that we identified, 10 of them contain 1 point of the spectrum. The rest are empty. All right, so let's try to push a little bit further. No. Okay, so approach to computing this function was in fact proposed in a work by Bombi in 1982. So Bombi, I believe he worked in Canada, and he gave a lot of very remarkable numerical results, or very remarkable estimates, and in particular, he also gave the first bound, the first estimate, lower and upper bound on the Hausdorff dimension of the Apollonian gasket, and all of them were completely accurate. So I feel that for some time we were following his footsteps, and we were not able to find any sort of inaccuracies or anything that would be wrong in his papers. So we're going to follow his strategy. Let's start from try to get a little bit of understanding of what is going to happen with these sets that are defined in terms of continued fractions. So one of the most well-known and most celebrated probably sets is a set of continued fractions that contains only digits 1 and 2. Dimension we now know very well, like Mark Polycott and Oliver Jenkinson got 100 decimal places. Then we later computed 200 decimal places, but for the purpose of this talk, it is sufficient to know that it is bigger than 0.53. And it is bounded, so it has the smallest point is square root of 3 minus 1, and it lies between square root of 3 minus 1/2. So it lies in the interval. Why this set is significant? What is the significance of this set? So if our sequence has only digits 1 and 2, then its Markov number is bigger than square root of 5. So this is the smallest Markov number that we know. And it is achieved, as one can easily see, at the sequence, the constant sequence of ones. On the other side, the largest Markov number that we can achieve using the digits of 1 and 2, it is going to be square root of 12. And it is achieved in the alternating sequences. So alternate that if you take 1, 2, 1, 2, 1, 2, then it is going to be the square root of the the supremum is going to be. Okay, so we're going to use these two insights into the set of digits E2 to try to understand how one can compute the upper bound and the lower bound. So we'll begin maybe by fixing some number, for example, t bigger than 0, positive number. And what we want to do, we want to construct a set of sequences, a finite set of sequences, in this case of 1 and 2s, so that it doesn't, if it doesn't contain a string from F, then the Hausdorff, then what we do know, then its Markov, that this Markov number is going to be smaller than t. So let's try again. So we fix the number t that we want to investigate, and we compose a set of continued fractions by computing continued fractions of all of the sequences that come to mind, and so that the Markov number of anything after we've excluded is going to be smaller than t. And the result that was used that we have here is by Moreira, that if you have such set, then if it doesn't contain a string from F, then the Hausdorff dimension of the Markov spectrum in the interval of square root of 5, from square root of 5 to t, is going to be the subset of this of the Descartes sum of 2 plus k plus k. This more or less by definition. It's not very difficult. Because our Markov numbers we obtain by taking okay, so there is the fact that there is in fact a sequence that supremum is achieved, that Markov number is going to be one of those, and this estimate on the estimate on the Hausdorff dimension just gives us that the inequality between the Hausdorff dimensions gives us what we wanted, more or less. Okay, so how can one use this insight? Well, for example, this insight was similar insight was used by Hall. Then he says that if you have a sequence of 1 and 2s that doesn't contain 1-to-1, then the Hausdorff the Markov number is going to be smaller than square root of 10. And what does it mean to us? It means that we can also compute the Hausdorff dimension of the strings of continued fraction of the set of continued fractions of digits 1 and 2, which doesn't contain 1-to-1. And it turns out that it is smaller than 0.45. And it tells us that the Hausdorff dimension of the Markov spectrum in the interval between 3 and square root of 10 is no bigger than 0.9. Why is this useful? Well, if we are looking that, okay, we are looking to determine, this is just an upper bound on our function for t equals to square root of 10. So this is not very good upper bound, but it is an upper bound. So computing upper bound on the functions that we are interested in some sense is very easy. So for any, we just pick a point, and if we manage to assemble a sufficiently manageable set F, so that Markov numbers for all sequences is this, once this set is eliminated, then Markov numbers are going to be smaller than t. Then this gives us the dimension of this set and gives us efficiently an upper bound on our function. So this is not, so that this is very approachable, especially if you have modern computer in hand. Lower bound was also developed, approach was also developed by Bombi, initial approach, but it is much trickier. So the truth is that we cannot, so it's very, it is not very easy, and not as easy as the upper bound. But it follows the same logic that if you have, if you can have a Markov number of strings which do not contain some subset F, then that for any, and we have the Hausdorff them, we can assemble the set the constant S. Then Moreira proved for us that the Hausdorff dimension of this Markov set in this interval is bounded by from below by twice of the dimension. So in fact, as a summary of this is that if you have any set of forbidden subsequences of any set of forbidden words, and we have a Hausdorff dimension of this set, then its Hausdorff dimension will give us an upper bound on the value of the dimension function at point where which we can determine by taking maximum of the Markov numbers, but it also gives us lower bound, but as a point that we don't know. It just gives us lower bound elsewhere. Okay. So this means to us that in order to, if we want to estimate the function, more or less, all we need to do is to compose many sequences of that we're going to call forbidden sequences of 1 and 2s. And what we're going to do, we're going to compute dimension of what is left from the set E2 after all these subsequences were eliminated. And this will give us upper bound where we want, and it will give us lower bound elsewhere. But the truth is that if we have sufficiently many digits, sufficiently many stopping points, so to say, then it doesn't matter where we compute the lower bound because it will give us lower bound somewhere, and we don't much care. This somewhere happen to be sufficiently dense. All right, so what does this mean in practice? So this is was done already by Perron, that if you know that if you take square root of 12, then for all sequences of 1 and 2s, Markov number is going to be smaller than square root of 12. Therefore, if we take empty set of forbidden sequences and we take E2 is the entire set, then the Hausdorff dimension of the Markov spectrum in this interval is going to be bounded from below. It is going to be bigger than 1, when it can be bigger than 1. So it does tell us that the transition point, that the spectrum, because the dimension of the spectrum became 1 before that. So this is, and now we go back to our computer and tell the computer that he needs to assemble a lot of sequences that are going to be forbidden sequences of 1 and 2s. And he's going to compute the Hausdorff dimension of what is left out of the set E2 once these sequences are eliminated. And we are going to try to compose, to assemble from the data that computer gives to us the graph of the function. So this is the strategy, which is more or less we realize. So I'm going to try to get a little bit more of this. So I try to, when I try to explain it for a paper, I try to draw the decision tree. So what is happening here is that we started the root. We started this number, And we think that, okay, you need to compose a set of sequences so that Markov numbers satisfy some inequality. So what we're going to do then you start, it picks with number 1. This is the first guess. You don't know anything. You have to start somewhere. And then it says that if your 1 is at 0 position, then this lambda function is going to be between square root of 3 and square root of 12 minus 1. So square root of 12 minus 1 is smaller than we wanted. So we are going to not consider these sequences as they are not of interest to us. Okay, then if it is not 1, then it should be 2. So we put 2 in the root here and say that, okay, our sequences are going to have 2 in the 0th position. Then what's happened here, let's try to see, it has to be something else. Then if it put 2 at the end, on the left-hand side, what's going to happen? Okay, now let's start with 2. 2 is good. 2 is smaller than square root of 12, which is expected. It has to be something. Now, if I put 2 after that in position number 1, then I can compute my lambda function. And I'm going to, and this turns out to be correct. It's going to be smaller than t again, so that it is square root plus 1, 4 plus 3 plus 1, and 2 plus 2 over square root of 3. So we are not going to follow this fruit, so to say, that we're not going to follow this branch. However, if we add 1 on the right, then our lambda function is going to be smaller than square root of 12. So the possible interval as the values of the lambda function is going to be square root of 12. And then we can grow the sequences by basically adding 1 or 2 on the left or on the right. And we're going to compute the value of possible values of the interval for the values of the lambda function once we added something. And then we're going to look for the strings so that its lambda by alpha is going to be guaranteed bigger than the value that we set up. And so we follow as our computer, and at some point we arrive at the 2 sequence 2, 1, 2, 1, 2. And this is the first sequence that we found out that we have to exclude in order to get in order to guarantee that our value is going to be bigger than t. So this is the strategy, and further you go, that the longer sequences you consider, more accurate bound you're going to get. But at some stage you have to stop somewhere because you have some limitations in your lifetime. So, for example, as the did set up 3 to 3.333, just a nice number, then eventually the computer comes up with these sequences. So I told that my computer to look up for all sequences up to the length 9. And the question now, of course, is that, okay, so here is a subset of E2, and this is a set that if we want to achieve our goal, we need to be able to compute this Hausdorff dimension somehow. So I have very little time left. Okay, but sorry, I will try to finish on time. Okay, so this is basically where we arrive. So if we follow the approach by Bambi, that if we want to compute, for example, the value of the dimension function anywhere, or if we want to compute the value when the dimension is equal to 1, then we need to be able to compute the Hausdorff dimension of a set of continued fractions that is defined using this rule. So it is a subset of E2 here. And all we know about it is that it contains all sequences, so that this particular choice of subsequences is forbidden. Okay, so if I have 5 minutes, I can tell you a little bit of how it is done. I have, but do I have 5 minutes? Okay, I have 5 minutes. I'm probably leave questions for later. I was about to ask the questions. Okay. All right. So this is a toy example. Again, so back to that I showed you before, that, for example, we have just digits, that's all sequences of 1 and 2s. And what we don't want, we want to consider sequences that don't contain 1 to 1 or 2 1 2. And what we do, what we know how to do. We construct a dynamical system so that the set we are interested in is the limit set of this dynamical system with this iterated function scheme. And for this particular choice of numbers, what we can do, we can take the Gauss map or second iteration of the branches of the Gauss map. That here G1 and G2 is just digits 1 and 2. And this is a Markov condition, so that it is so-called graph-directed Markov system. And our limit set that we are interested in, this is a set of all continued fractions, if you don't contain 1 to 1 and 2 1 2, is going to be the limit set of this dynamical system, which consists of 4 maps, T11, T12, T21, and T22. And this is also this Markov condition defined by this Markov matrix. And therefore, the Hausdorff dimension of the set that we're interested in is, in fact, the Hausdorff dimension of this limit set of this iterated function scheme. Okay, and as we have Mark explained in his talk earlier, then one of the approaches that we started for computing the Hausdorff dimension that we boils to computing the spectral radius of the transfer operator. And one approach to this that we learned, in fact, from the great men of the past, that rather than computing the spectral radius, what you can do, you can compute the eigenfunction, and then or compute approximation to the eigenfunction, and then using the fact that it is isolated eigenvalue, you can estimate that you can prove that you can get estimate of the eigenvalue of the true operator. So here we construct approximation to the eigenfunction in the Chebyshev Lagrange basis, and by computing eigenvector of the matrix, which is projection of the matrix of the projection of our operator onto Chebyshev Lagrange basis, and this is how it looks like. So this is an action, one of the elementary metrics, which is an action of the transfer operator on the basis elements, and it's a small matrix, and we assemble several small matrices together. We get a matrix taking into account Markov condition, and what happens to us is that if we have left eigenvector of the matrix that we assemble, then it gives us a good approximation, or sufficiently good approximation to the eigenfunction, so that we can obtain estimate on the spectral radius, and consequently we can obtain estimate on the dimension. Okay, the strategy is very good. Practical realizations has a few problems in this case. So the first problem is that you need to consider very, very long sequences. And if you try to keep this matrix in the memory, if you try to keep full matrix in the memory, then the first rough estimate, if your computer, my computer didn't like it much, and that says that we need just 2 gigabytes. And this is just going to be Markov matrix, but you need to compute the dimensions. So you need to keep actually much bigger matrix because it will be like about terabyte. What is the good news about this matrix is that if your sequence, there are not too many sequences, so they can be very long, but there are not too many of them, then what happens is that the matrix has a lot of similarities. So that's a lot of rows in this matrix are the same. There's a lot of columns in this matrix are the same. So rather than keeping in the memory full matrix, which will be a size of a couple of millions, in fact, all you need to do, or it turns out that it is sufficient to keep a matrix of the size of 229, for example, for this particular case. So this was this is why at first sight the problem appeared to be impossible, because if you have a matrix that takes more than a terabyte, and you are interested in computing this Hausdorff, it's eigenvector, you're not going to be very lucky probably. But in fact, the structure of the problem allows us a lot of memory saving and a lot of reductions happening here. And therefore, this is and this makes it eventually possible, and you can do it for all over again. So this allows us to realize more or less this strategy for all possible for the values of t that we are interested in, for 1,000 values of t, and thus we obtain approximation to the dimension function. Okay. Okay, let me thank organizers for inviting me here. I finish my talk now, and yeah. Any questions? I'm happy to take.
Indeed. Are there any questions?
What kind of precision do you get on the value of the dimension?
On the value of the dimension, currently we limit ourselves to 4 digits. So so for the function itself, just because we wanted to do it in a finite time, I suppose, we decided that we're going to stop at 4 digits. But in principle, you can get further, but it will just take longer.
Okay, but with current computers, how far could you get if you wanted one precise point?
If you want one precise point so here we get 6 digits, and it involved sequences of 24. And our estimate, as far as I remember, that if you want to get more digits, then you will need to take longer sequences. So unfortunately, I don't know what the current computer allows. But I imagine that for any 2 digits further, so the structure is going to be more involved. So I really don't know how far you can push. But I imagine that I would be very much surprised if you can get more than 8. Just because you need to, because if you want to get 4 digits here, I think we could get away with sequences of the length 12. But no, sorry, if I need 4 digits, I could get away with the sequences of the length 14. But in order to get 6 digits, I had to go to we had to consider sequences of length 24. So just to give you an idea. So I imagine that if you want to get 2 more digits, you probably will need to get another 10. So probably need to get to sequences of length 34, and I don't really know what the current computer allows. But it is parallelizable, of course. This is a good news.
Are there any more questions? If not, let's thank the speaker again. Welcome back, everybody. So the next talk will be by Damien Thomine, who will talk about formalizing topological entropy in Lean. Please.
So, thank you very much. So thank you very much for this inviting me to this very nice conference. So what I would present is a talk about proof assistant and proof verification using Lean. So it will be in the continuation of Sebastian's talk on Tuesday. So I will present a project, and it's personal project. What I wanted to try is to prove this formula. That is, if you have a subshift of finite type, its topological entropy is equal to the log of the spectral radius of the transition matrix. So this is something very standard, and essentially there are 3 steps. The first one is you need a notion of topological entropy. Otherwise, the left-hand side has no real meaning. And then you need performance theory to get a handle on the spectral radius of the transition matrix. And once you have these 2 ingredients, you can more or less conclude, and the conclusion should be comparatively quite easy. So this project is not finished as of yet. I have a notion of topological entropy which is formalized, and it is usable enough to be applied to the full shift. So I have this formula for the full shift, which is quite easier to prove and doesn't require the second step. So basically, what is done is the first step is finished, and I will explain a bit more. So before I start to explain what I did in this project, what I wanted to address is why have these kind of projects. And the idea is you're new to Lean, you're a bit interested in proof verification, and you've completed the natural number games and small exercises like that. And it's a good idea to have a bit more complex projects. And why so? Because it's fun. I mean, using Lean is fun, and these are mathematics you like, and you want to see how to implement them in Lean, and this is a good motivation. It's also a very good way to learn the language, because working with a natural number game, it's a good way to handle the basics of the language, but what you don't get are the more finer things, specialized part of the library, how to build a project, because completing something which somebody has prepared for you is easy, but trying to build your own lemma, structure your files, it's separate skills. Contributing to MATLib is a separate thing. And there's a third reason, which I think is a bit deeper, is that it gives you some long-term goal. And I think it is a very good reason to have a bit more evolved project, because in Lean, one major concern is the usability of your lemmas. You need to write things which you can actually use in other proofs. And if you just want to implement the definition of topological entropy, I can do it in 5 lines. This is not the problem. The problem is building a kind of ecosystem around all the lemmas around to be able to get a handle of topological entropy and be able to compute on topological entropy for specific systems. So just to give you one example, and it will so on Tuesday, Sebastian said that one major concern in Lean was that Lean can check your proofs, but your definition you need to be careful about your definition, because if you are not, you can prove everything you want about things which make no sense. And he showed this with is compact, where nothing is compact, but I will give you a bit more kind of different examples. Maybe I can zoom a little. Yeah. So this is a definition of topological entropy. This is not the one it's not exactly this way I implemented it, thankfully, but I could say, okay, I've written this definition, I have a definition of topological entropy in Lean, and at this point, okay, you really have to trust me. So I will explain why this is a somewhat natural definition. So yeah, there's a way to write definition in so that they can be a bit more understandable than this atrocious thing. And so if I have this definition, the problem is then I want to compute the entropy of a full shift, and this entropy will be this atrocious thing, and I don't know how to do anything. So these long-term goals, they tell me that I have to write something useful. That's the first thing. It will be understandable and usable. And maybe there's a second consequence, which I think interesting, is that gives you some models, some objects you want to be able to work on. So for me, it was, for instance, I think my definition should be able to handle subshift, of course, because that's my end goal. And it should be able to handle, say, some axiom R things. And that sounds natural, but I will see that this has some implication on the choice you make for your when you design your project. So this is a project, and the current state, I have about 13 files with about 4,000 lines of code. I mean, it's a upper bound. It's the right order, but the true length is a bit lower. And these 13 files were divided in basically 3 sets. There's one set is just to fill holes in MATLAB. That is, I need other results which are not in the library. So, well, I write them myself and add them to the common library. This represents 4 files. I have 3 or 4, what I say core files, which are the files where I define the topological entropy and its basic properties. And then 5 files which are pretty short, which are just examples. That is the topological entropy of a product, the topological entropy of a union, topological entropy of a full shift, for instance. So that's 13 files and 4,000 lines of code. The true content for definition of topological entropy, it's this one, which are about maybe 1/3 of the total. And this project, it's not yet on MATLAB. It's hosted on GitHub, on another GitHub page, along with other project in Dynamics. And we will just cut it in small pieces and put it on MATLAB progressively, because if we put the whole 4,000 lines at once, somebody won't really appreciate it, I think. So that's the current state of the project. Now for my talk, what I would like to try with this talk is that when you're working with MATLib, as I think basically 4 people or objects which matters. So yourself and what you like, the mathematical theory, like you can find it in a book and in references. There's the Lean language, which has its own setting, its own constraints. And there's the community of user in Lean and the mathematical library, which is separate things. And all this thing will influence your decisions and the way you design things. And my goal is to explain how this interaction led me to various design decisions on topological entropy, because the definition I implemented of topological entropy is maybe not the one you're familiar with. Or I mean, it's a definition you're familiar with, but with a lot of small quirks. So that's what I want to spend some time on, these design decisions. First, the decision is what kind of topological entropy you want to implement. There are many definitions. There's a basic definition with open covers, which has the advantage to work on any topological space. There's the Bowen-Dinaberg's entropy, so which use the metric and an epsilon covers and epsilon separated sets. There's the compact entropy, which is based anyway on the Bowen-Dinaberg entropy. You have notions of entropy on non-compact sets, which are closer to a kind of Hausdorff dimension. You have notion of entropy for non-autonomous system. You have a notion of entropy for action of amenable groups. And so when you use a proof assistant, writing the proof is long. So Sebastian talked about 10 factors between what you write on paper and what you write in Lean. Lean is a bit unforgiving. So when you write a proof on paper or explain it to a colleague, you can say, okay, this works the same, or this can be generalized, and Lean is not really convinced by hand-waving. And so one goal is to have a somewhat really general framework which can be used in many settings, because if you have a very specialized framework, it works, and then you need an example which is a bit outside, you have to rework everything, and it's pretty long. So there's always a compromise between generality and ease of explanation, even when you writing a research paper or teaching a course. And it's not extreme. You won't try to do a notion of which covers everything here, but it still tilts the balance towards generality, I would say. And this has led to, I think, some kind of, well, you tend to encounter a lot of Bourbaki in some part of the MATLib, the library. We'll see some examples in a few moments. So anyway, here, the problem is I don't have a natural general notion which will cover everything. So I have a choice to make. And this choice, I think the important criterion for me was to be usable. I wanted to actually use it to compute the topological entropy of a specific system. And in this case, the more natural choice is Bowen-Dinaberg notion of entropy. And this, for now, the way it's implemented, most applications are penless. I mean, very close to mathematical thinking. So for the examples, they can be worked on very naturally. There are still some problem to solve, but that's. So this is maybe the first design decision, that is which kind of entropy I implement. So for instance, open cover, the entropy of open cover will be easier to implement, but harder to use. So this is a good compromise, I think. The second design decision, and I will have to explain a few things. If you look at almost all references on topological entropy, you will get something like that. So this is from 1971 article by Bowen. So topological entropy, you define it not with a big definition at once, you do it in several steps. So the first one is you define so-called dynamical balls. So this is Bn of x epsilon. It's a set of y. So that d of tkx, tky is smaller than epsilon for all cos this thing. So you define this ball. So you work, for instance, on a compact metric space. You define these balls. You defined a notion, so for instance, is the minimal cardinal of n epsilon of a cover by n epsilon dynamical balls. Then you take, so you define, for instance, h bar of epsilon, which is the lim sup of the logarithm of this over n. And finally, your topological entropy, it's you take the limit when epsilon goes to 0 of this quantity. So this is the presentation you find. This is the presentation you find even in early articles. And what I call here this h bar of epsilon, for instance, is exactly this quantity here. And already, that's what I will do in MATLAB. So maybe a bit more steps. Instead of writing a big definition, I will just work progressively and introduce different objects. Maybe one difficulty I have with introducing different objects is that in MATLAB, you need to give a name to everything. So I need to give a name to dynamical balls, which is easy, but I need to give a name to this and to this and to this, and it's not always clear what the right name for this object is. Anyway, wrong computer. Yeah, so this is definition of topological entropy. This has one downside. This definition has one downside is that topological entropy is a topological invariant. That means if you have a topological conjugacy between two dynamical systems, the topological entropy is the same. But this definition involves a metric. And so you can probably get that very easily that it's an invariant by isometry. It's natural, but if you define it this way, there's something a bit uncomfortable. That is, if I take a compact space, for instance, without a metric and a continuous map on it, its topological entropy is well defined. I put a metric and then I do the computation, and it won't depend on the metric. So actually, maybe I don't have to introduce a metric. So how can you speak about topological entropy? How can you do this construction without introducing a metric? There's a solution. Is to use what is called the uniform structure. So we'll explain what is it. This is not a big secret. I mean, it's not the definition you will tend to see because uniform structure are not something which is very well known. But it's not a secret ever. I mean, you can find this on a remark on Wikipedia. So. And at this point, I think I need to explain what is a uniform structure because otherwise you won't really understand what's happening. So for if you have a metric space, 2 points x and y are closed if their distance is small. So distance is small, that is, for instance, distance smaller than epsilon for small epsilon. So what does this mean? It means that if you look at x times x, your point of coordinate xy must be in a very small neighborhood of the diagonal. So it's neighborhood here with size epsilon. So what we can do is to abstract this intuition, and we forget about the metric. What we are given is only this family of neighborhoods of the diagonal. And then 2 points x and y are closed if this pair belongs to a small neighborhood of the diagonal. So this doesn't, we don't need a metric to do this thing. We have some operation on neighborhoods of diagonal to emulate what happens for metric spaces. So for instance, we can assume that the neighborhoods are symmetric, which emulates the fact that the metric is the distance is symmetric. We have a version of a triangular inequality. There is an ability to split epsilons also. You can split epsilons in two. So there's a lot of arguments you can do on metric space where you actually only need a uniform structure. And the nice point, if you're working on compact space, yeah, yeah. Not always. I mean, if you have a topology, you wanted to induce a topology, but there are many uniform in that. Yeah, it's stronger than a topology, but weaker than a metric. So for instance, if you have a compact space, there is basically only one uniform structure which is compatible with the topology, is to take all the neighborhood of the diagonal. If you're non-compact, it's a bit more complicated because how we behave at infinity can be different. So this neighborhood of the diagonal, they call the uniformity or entourage. And now, how do I write a dynamical ball? I will look at the set of xy's, which such that their iterates are closed until time n. So that is equivalent of dynamical ball, and I can write it a bit in a bit shorter way in this way. But this is the same definition. And maybe now I can go back to this definition here, and we see that the first definition, is exactly what I've written here. So this is, I said UN. This is exactly what is written here. So the symbols are much the same. This means that K is strictly smaller than N, and this is just, I mean, you can see the parallel with what I've written. And once there's this, the second definition is the definition of a cover. And the third definition, I mean, it follows what I've written. So the definition of a cover by dynamical balls, the definition of the minimal cardinal, the lim sup. So this one is pretty easy to see. And finally, I take not the limits when epsilon goes to 0 or u converges to the diagonal. I just take the supremum because this is monotonic. And this is this, instead of having one big definition, you like this, you have 5 definitions and things are much more tractable, but this is natural. This is what you're doing in when you write mathematics. So if you are a bit frightened about uniform structure, I want to thank one nice thing is okay, just I will show you this way. The documentation on MATLib is quite very well written. So for you have all the explanation you need, not only on the mathematical side, but also on how to manipulate it on in MATLib with the references. So when I say that there's some kind of review for Baki, it's so yeah, I can't. Maybe I can do it in this way, so that you. We try something. No. And maybe I can do this, so you can see what. Sorry. Yeah. So there is a very well written documentation on uniform spaces, which explains the mathematics and how to use it in MATLib. So this is absolutely perfect as a reference. You can also find Sebastian talk about filters. You can find references on filters. I would just, if you're not used to filters, Patrick Massot has how to use, which explains the mathematics of filters and how to use them in MATLib. So there are documents for you if you are not familiar with these subjects. Anyway, I will go back to my presentation. So now the second design decision was to use uniform spaces. What is okay? What is the problem here? Let's see. Okay. So there's a third design decision, which I think was the right one, but which was very painful, is to what kind of number I use. So for topological entropy, plus infinity is a perfectly valid value. So for instance, if you take a shift on the interval 0, 1, you get topological entropy of plus infinity. So I wanted to have a notion of topological entropy, which gives me, okay, this entropy is plus infinity. The thing which is a bit less evident, the entropy can be negative, and minus infinity is a perfectly valid value for topological entropy if you're looking at the empty set. It's basically for the same kind of consideration for why the degree of the zero polynomial is minus infinity. For instance, you want this formula, the topological entropy of a product is the sum of the topological entropy. If your S is an empty set, the empty dynamical system, you get this thing, this identity, and either it's plus infinity or minus infinity, but minus infinity makes more sense for other reasons. So this is the third design decision. We want the topological entropy to take the value not in the real, but in the extended reals. So with minus and plus infinity. Actually, it takes value in a kind of convex cone, which is minus infinity union 0 plus infinity. And there are other various decisions in this way, like the minimal cardinal, it can be plus infinity. If you have no cover, the minimal cardinal is plus infinity, for instance. So, and I also use the extended non-negative real 0 plus infinity. So it makes, at the end, everything is much cleaner. So supremum, lemma, flip sub, they always exist. The statements are very clean with very few exceptions, but there's two downsides. The first is that MATLib does not have much to say about extended real numbers. There's some lemmas, but there are lots more to implement. So I told you at the beginning that there was 4 files about holes where I was filling holes in MATLib. It's mostly about extended reals. And the second problem is some kind of coercion hell. So I will explain very quickly what I mean by that. When you're working with, I'm working with different kind of numbers. And for MATLib, for instance, so I'm working with this kind of number. I have the natural somewhere. The natural, they can be sent into the extended naturals. We can be sent into the extended positive real, we can be sent into the extended reals. And somewhere I also have the real somewhere we can appear. And for lean, these are all different numbers. So for instance, if I have one, the natural number 1, it's not the same thing as the one in the extended naturals, which is not the same thing as this one here, this one here, this one here. You can think of it as we always make explicit this kind of injections. And now, for instance, this kind of lim sup of log over n, actually, so it is written like this. But actually, what is behind is something a bit more complicated. It's actually the logarithm composed with an injection, composed with this function mincard. And this thing I multiply by this injection, composed with this thing. So I have so the formula actually is like that. That is, at some point, I take this as an extended natural, and then I convert it to an extended real before applying the logarithm. And there's a lot of small decisions like this, which makes your formula actually pretty more complex than what you would expect, and much more difficult to manipulate. So this is something which is not completely fixed at the moment. I will still run computer. And this is something I will talk about if I have time. How much time is left? Okay, perfect. So I have time to show you actually this kind of question. They were apparent in the file. I show you. So this kind of question will appear, for instance, here. I can zoom a bit more. Here I take the cardinal of a finite set, so it's natural number. I said, no, you convert it to an extended natural. Here you can see this. Here. Yeah, no, this one is fine. Here you see you have a natural number. This natural number, you're going to convert it to an extended positive real number. So this is what is written here, and there's some more questions which are not shown in the file. But that explains maybe some of the things you saw in the definitions. This is what they mean. So this is the third major decision, I think. No, the fourth one. I will talk about the restriction of maps to a subset. When you're working with dynamical system, quite often you're not working on the whole map, you're restricting a map to a subset. So for instance, a subshift is just a restriction of full shift to an invariant, to a specific invariant subset. The Lorentz attractor, it's you can just study for itself that is restrict the Lorentz flow to the attractor. If you have an axiom A flow, you can restrict the flow to its hyperbolic set. And sorry. Okay, it seems it works half the time. So we are many dynamical systems defined as restriction of a larger system to a specific subset you're interested in. And in Lean, this kind of restriction means you're working with subtypes. So in the same way that the one of natural number is not the same thing as the one of the extended natural number, if you have a subset of a larger set, an element of F is not the same thing as an element of X. It's an element of X, it's an element of X plus the property that it belongs to F. And this sounds a bit stupid, but the problem is that when you're, since it's another set, you can approve a lot of properties on X, like it's a manifold and you have many tools and so on. Or it's a shift and you have a notion of cylinder and so on, and you do that and you restrict it and you have nothing on the subset. You have something, but you have to work so that any object you have on the whole system, you can define them on the subsystem. And it can be very long, very painful. So for instance, I have a uniform structure on X. You can restrict it to uniform structure on F, but it's not obvious if you can manipulate this, and it's very, very, very painful. And again, I will show you. So for instance, if F is invariant, you can restrict the map to F, but the restriction of the map, it has a formula which is a bit annoying. And I think it's worthwhile. I will go again to this file. And I need to, this is a definition of the induced map. I don't use T. The induced map is T plus you need to specify the new domain, it's F. You need to specify the codomain, it's F, and you need to provide Lean with an argument that says that, yeah, if I start from F, I'm still staying in F. And so you have this new map, and then you have very stupid thing to show. So for instance, the iterate of this map, is it the restriction of the iterate? So do you have something like TFFN is equal to TNFF? This is true, but this is something to prove, and this kind of small things, they are everywhere. So the main lesson is to avoid as much as possible to work with subtypes. I think this is something which was done also for groups. That is, you try when you have subgroups, is to try to avoid with subtypes. So you use some tricks which I think are pretty close to what I decide to do. So the third major decision was instead of, so just one last word before yeah, this doesn't work. The second time is a charm. Yeah. Where was it? Where was I? Yeah, so when you define the entropy of a subset, so what is done in most references, you define the entropy of a dynamical system. And then if you have F, which is invariant, you just say that this is the entropy of the subsystem is just the entropy of the restriction of the map to this subsystem. And as I told you, this is not something I want to use in Lean. So what I did instead is to define from the start the entropy of a subset of the whole space. So this makes the definition a bit heavier, but in the end, this is what you have to do. That means if you try to think about what is this object, it depends on a topology or a metric. So all the objects you have to get from the whole space X. And when you try to unfold of the definition, in the end, this is kind of what you have to do anyway. So at least we might as well do it from the start. So this is maybe the fourth major decision is instead of defining the entropy of a whole system, we will define the entropy of any part subset of the phase space. And to ensure that this is the same thing as the usual way, I will add a lemma at the end to more like an aesthetic lemma, I think, to say that, yeah, this quantity I've computed is the same as the one you used to do when you restrict. But this will be pretty painless because it will be only one point in the whole file, and everything else I don't work with these restrictions. So this has maybe the four major decisions. Each major decision, it's quite a lot of work because most of the decisions, you don't get them from the start. You write in a file and you see that you have some problems, and then you change this thing at the beginning, and you have to rewrite basically everything. So the main file where I define the topological entropy, I have to completely write them like 4 or 5 times. For instance, this problem, I noticed it pretty late actually. So if you do this, you have to change all the definitions. So this has maybe the major decision, and for each major decision, there are many more smaller decisions that maybe you do a bit everywhere and you notice less. For instance, even the definition of a separated set of a cover has a few quirks. So for instance, for the definition of a cover, problem is I want to cover F by dynamical balls. And since I'm working on a subset of the whole space, I have 2 choices I can make. Can ever say that all the balls have to be centered on F, or I can choose to say, okay, they just have to be somewhere in the whole space. So this has 2 different definitions. And in the end, they give you the same theory. You can prove that the quantity you define one way or another, they will give you the same quantity at the end. And this is not completely trivial. This requires some work. And there's not one definition which is really more natural than the other. This one, for instance, they behaves well when you take conjugacies or semi-conjugacies. This one behaves well when you're trying to prove that the entropy of a larger set is larger than the entropy of the smaller set. Because, for instance, if you use this definition and you try to prove that the entropy of J is larger than the entropy of F, well, J is larger, so you may think you need more balls, but at the end, you also have more freedom to put these balls, so it's not completely obvious at first that your entropy increase with the set. So this is this small kind of decision. They are a bit everywhere in the file. So this one, in the end, I chose the second definition. Why? Because the definition is shorter. I don't need to check that the balls are centered on F, so it's easier to use. And in the end, it's a bit what matters. So I think this is what I wanted to talk about, this kind of design decision. So different design decision and how they are influenced either by lean, so try to avoid subtypes, or by the mathematical library. The library on uniform space is very well developed. If it wasn't here, I would have probably used metric spaces, for instance. And now I want to share some point of to conclude on a few points. So first, I will go a bit on the state of the project. So what is done? It's monotonicities, entropy of a closure, entropy of images under semi-conjugacy. I will just say a few words about this, and entropy of full shift. So this is done. Partially done is entropy of a product and entropy of a union. And at some point, I was the proof were getting messy, so I just go for something else. And we should start putting some pieces here and there on MATLAB. And I want to show you a couple of things. So I will go back to last time to this Word file, and instead of this, I will go. So here you have all the files. So as I told you, I have some files to complete the extended real numbers. So here, for instance, I have a definition of the logarithm of plus infinity or logarithm of 0. I have a division. I have the continuity of the multiplication on the extended reals, which is extremely annoying to prove. Then afterwards, I have three files where I define the entropy of covers, the entropy of by nets. The end is not what matters. What matters yeah, beginning. So and definition file just for uniform for the dynamical balls. And I have all these applications. And I wanted to show two of them. The one is a shift, because the first check for the first part of my project was, can I compute the entropy of a full shift? And yeah, that works. So the definition are maybe a bit wonky, but especially this one, which I should replace by something more natural, but it works. And the second thing is sometimes, as I said, I work with uniform spaces, and sometimes you are good surprises. Like you're feeling you're doing the right, you have the right theory. So maybe one comment. In general, in books, the topological entropy is defined for continuous map on a compact space. Here, compactness basically doesn't appear, and continuity very rarely appear. So about most of the lemma just for an arbitrary map on arbitrary space with a uniform structure, and it requires more work, but it's worth it. So there is one thing which I think was very nice, and here this is this thing here, and we explain one last mathematical thing. So something which is interesting is when you have morphism of dynamical systems. So when you have a commuting map, and you take a subset here, and you look at its image here, downside, and what you know is that the topological entropy of this is smaller than the topological entropy of this. What is less known is that the topological entropy of this is equal to the topological entropy of this. Because you have one variable you can play on, it's a uniform structure. So what is true is that if you have a uniform structure here, the topological entropy of this set for this uniform structure is equal to the topological entropy of this set for the pullback of the uniform structure. It's quite natural, but I mean, it's very clean explained that way. And this is exactly this lemma here. The entropy of the image of F is equal to the entropy of F with a very specific uniform filter. And I like it because the statement is very simple and it has very nice consequences. So for instance, if phi is uniformly continuous, you can, phi is uniformly continuous, it tells you that this thing is smaller than the uniform structure, natural uniform structure at the source. And it tells you that the topological entropy of this thing is larger than the topological entropy here. So you have in essentially one, I think it's a one-liner. You have the, no, it's a two-liner. You have the statement you are most used to. And it's not only a generalization of, it generalizes this statement in another nice way, is when you have a subset of f of x, you have an inclusion map from f to x, and then I use for phi this inclusion map. And what is nice is that gives me also very quickly that the entropy of the restriction map is exactly what I expect it to be. So this is the entropy in the way we use it. So it's the h top of the restricted transformation. This is my version, and I have also very quickly that the two are equal. So this statement, it's I think it was a very good surprise and generalizes a few facts about topological entropy. So I was quite glad to have it. How much time? Okay, I think it will be less than 5 minutes. I will just say a few words of conclusion. And it won't work this. Oh, yes, it works on the first time. So this is the start of the project, the state of the project. What is lacking? What is lacking is this question is extremely cumbersome. What I've not shown you is maybe 20 lines or more to prove that log 2 over n converges to 0, which is not something you want. So one way to, what I would like to do is to write at some point some file to completely avoid this question hell. And one way to do it would be to have some kind of notion of exponential growth. So for a sequence, it would be define an object which is a lem sup of log of un over n, and prove many facts about this quantity, and use this fact just to avoid all the annoying computation for topological entropy, and it can be reused in other contexts very easily. So that's one goal, is to avoid the painful parts. For myself, afterwards, I will continue to perform Frobenius and subshift, I think, but there are still many low-hanging fruits for beginners. Topological entropy in MATLAB is not very well developed, so a lot of small things you can try if you want. So entropy of the subshift is what I will do, but for instance, I have nothing about the entropy of iterate of a map, something which I will have to make. Entropy of flows is nowhere. There are other definition of topological entropy you want to implement. You want maybe topological pressure. All these things are not in the not yet done. You have also notion of metric entropy and variational principle, which are also very nice long-term goals. There are many things to do before. And I will end this talk on a pretty different remark. So I will talk a lot about this project and how I interacted with Lynn. What I want to do to share at the end is how Lynn interacts with me. So I have a feeling, it's pretty personal, that working with Lean has also changed a bit the way I do mathematics. Not a lot, but still in a noticeable way. So for instance, a more structuralist way of thinking, so you don't really care about definition, you care about the properties, about the object you defined and how you can manipulate them. And you care about statements which lets you prove things, also maybe more care to what theorems are really applicable to a specific situation. And also maybe a better ability to detect some statements which are very clean, relatively straightforward to prove, and which can be used in efficient way. So it's pretty subtle, but I think it has really influenced a bit my teaching and also on the research side. It's I mean, this is something which we aim for when we use Lean with students in first or second year. There are courses of Lean to make them understand basic logic and manipulation of quantifier and so on. But even as a level, I think it has a non-negligible influence. And to end, I would like to thank so Sébastien and Patrick for introducing me to computer-assisted proof, and all the nice folk at the BUT projects for their help, and hopefully this will be put on MATLAB soon enough.
Are there any questions or any comments?
Thank you for the talk. I'm curious about this coercion problem. So in some sense, the problem is that Lean is too explicit. So you need to prove some sort of theorem that tells you that the two objects, that one in the extended reals and one in the normal reals.
Yeah.
The normal reals are the same. So that's the point.
Yeah, that's basically the point. So for instance, you have an addition, and you have maybe some very nice property for addition on the reals, and then you work to the extended reals, and you need to reprove the same statement. So you have many things you need to prove in parallel.
So Lean has not some sort of a substitution engine that just says, okay, in this specific case, these two objects are the same, so you can just substitute
I
them.
mean, for some basic things you have. So
Mhm.
for instance, if you have a function from X to Y, you can apply it to an object in small f, because it will understand that actually, okay, it's behind by an object in X, and I can apply this function. But so for very simple things, it works. But when you're talking about, say, continuity, problem of continuity and limits, it just breaks down, and you have to do things really by hand. There's some properties which are very nice on the natural, for instance, and not true in the extended reals. So, and maybe there's something larger than the extended reals that we would like to. No, no. We really have a different structure which are a bit separate, and this inclusion map between each of them. It's pretty rigid, very pedantic, and sometimes painful. But
Are there any more questions or any more comments?
Yeah, I suppose that, like, as a subset of this, you have these subtypes, and really it seems like very little about, you have to reprove everything for the subtypes of some. So I mean, that was about supertypes, but my question is about subtypes. So is there any sort of move in Lean towards, for example, making it easier to define subtypes? I mean, are there people working on getting rid of some of these pedantic obstructions?
I would say yes, and things have been much better, for instance, with Lean 4 than it was with Lean 3, and on this side. It just, I think it just so when I was saying I'm interested, for instance, in continuity and so on, and this is just so far away from what I mean, the concept is so far away from what we need that it's But yeah, it's better to do things yourself and just try to avoid the difficulty.
Are there any more questions?
So there are different lean versions. Is lean 4 backwards compatible to lean 3?
It's not backward compatible, but there is automated scripts to put things to convert things from lean 3 files to lean 4 files. But basically nowadays everybody uses lean 4, so lean 3 is history.
Yes. So nothing needs to be rewritten again in lean 4 that
I mean, the script was not perfect, and there was a lot of things to to fiddle with, but it was still very efficient.
Thank you. Are there any more questions? Any more comments? Any more thoughts? Oh, excellent.
Okay. You already said a bit about this, but I'm curious, the process of formalizing all of this mathematics in Lean, what were the highlights of the, or if any, the more understanding or surprises of the mathematics during the process?
So I think two surprises. So this one, I think I was thinking it was really nice because it was at the end of this project, and at some point you have a very clean statement which generalizes many interesting properties, and you have a feeling that you have done the things the right way when you see this. And the second thing is, as I told you, everything is defined for arbitrary types, and so not necessarily. So what I mean is that I don't work necessarily on a compact space, and for maps which are not necessarily continuous, and there is actually not that many statements which needs continuity. So you have a lot of things with not that many hypotheses, and in the end, it's pretty clean. So this was also pretty satisfying.
About this, you just said about no compactness. When you have, for instance, a statement about that, does it have any restriction on the existence of the limits? I mean, as long as the limits exist, then you have something. How is it?
So in very often you want to try to prove a very general statement, and sometimes the statement has no real meaning, and then your theorem will have some additional hypothesis. And just what I said in this case is most of the time I just don't have this additional hypothesis. Really, most of the theorem I don't need continuity, I don't need compactness. It just works naturally. For instance, if you have a non-compact system, what can happen depending on your uniform structure is you have no finite cover. If this is the case, then the entropy will be plus infinity, but this is not a problem because it's coherent with all the theories. So it was pretty well on this side.
Are there any more questions? Ah.
So you've formalized things with uniform structures, which I think is a good choice. But did you think of the people who don't know what a uniform structure is and who just know metric spaces? Is there some API to translate your?
Not yet, but I think it will. Yeah, not yet, but I think it will be rather easy to work out. So, but uniform spaces is the right way to do it. I mean, even practically, there's some statements which are, I think, easier to prove with uniform spaces than with metric spaces. For instance, for subshifts or for full shifts, I mean, you want to introduce cylinders with uniform spaces. What you are doing is you are introducing this set. So the definition of this cylindrical uniformity is very simple, very easy to prove with very nice property, and actually it works a bit better than trying to define the specific cylinders.
Aha.
So how much do you think that your program is near to being the minimal length program that generates this statement? Because in some sense, Lean with your program is like a Turing machine that is generating mathematics. So we can, in principle, try to compute the algorithmic information content.
I mean, that's not really my concern, actually. So, for instance, just to start at the beginning of my definition, I can get a very short definition, but how are you convinced that is actually the definition of topological entropy? So shortness is not really the point. The point is also readability and easiness to use. So I had a lot of small lemmas which just make things the life easier. That's the point. The only point where for now where we'll have to work on this kind of exponential growth, where I expect that we build a small library which will be very useful and will really compact the proof in the statement.
Thank you so much.
Are there any final questions? Excellent.
Yeah, I was worried a little bit about this remark on matrix spaces. So if you have a metric space, you have a metric structure, you have a uniform structure. So what's the problem? I mean, is it easy to add a kind of lemma so that idiots who want still to work with metric spaces can ignore uniform spaces, or is there?
No, it's pretty easy to. I mean, if people are interested in it, we can put it in a to-do list, and it should not be too hard to.
Usually, you put in a to-do list things that you really cannot do today. But it's simple. This is it's not going to create problems like you have to several types of things and.
No. This should be easy.
Thank you.
Are there any more questions? Anyone like to make any comments? Okay, since this was the last formal talk, we should thank the organizers for this delightful conference. That is Jean-René, Stefano, and Sebastian.